Welcome to HB Tuners Subaru Training Part 11. In this training video, we're going to be taking a look at the differences between a lambda reading and an air fuel reading. We're looking at a wideband display, as well as stoichiometric points for different fuel types we might be calibrating and tuning with. We have a lot to talk about. Let's jump into our video so we can check this out.
Okay, so let's get started. We're going to be taking a look at understanding the differences between a lambda reading, a wideband air fuel display reading, and the stoichiometric ratio of the fuel type that we're going to be calibrating and tuning on. How they all fit together. There's going to be a couple different segments here that we're going to be taking a look at, looking at our VCM scanner, looking at the VCM editor, and as well as looking at our Excel spreadsheet calculator from our course packet. First thing I want to do is just take a look at a sample file. Doesn't matter which sample file you have open. I'm in the sample calibration file from our Subaru course folder. I have one of the files open. If I could jump in here to engine, and I move in here to fuel, and I move in here to open loop base. We have our base fueling tables. These establish what the target air fuel or the target lambda is going to be. Let's take a look here. Jump into the alt table. We're going to find that this table here is based on engine speed versus engine load. Now, taking a look here, 0.3 to roughly 1.1, 1.3 here. This is our normal part throttle type of environment we're going to be finding we're going to be driving, and we're specifying that we want to run 14.7 to 1 air fuel. Now this represents the stoichiometric ratio for petrol fuel or pure petrol fuel. So this is what we'd want to go ahead and target. Now as we start to get into boost, we can see here, we start to transition into these higher engine loads, typically over 1.3 grams per rev. We're getting into an appreciable amount of boost, a couple pounds of boost. And we're going to find that we eventually start to go and command a richer mixture. And we're finding the air fuel here goes to a lower value. Now, as we're looking at this table here, we're going to find at the top, we can change this between air fuel, and this is going to be changing a different stoich point. We're going to find that depending on what we're clicking on here, there's going to be a units of lambda, which we're going to be discussing here. There's going to be units of phi, which is going to be the inverse to lambda. And then we find here, there's air fuel. This is going to be for methanol. This is going to be for ethanol. And then we come back here to different petrol blends. And we're going to find that, again, depending on what we're looking at here in terms of the air fuel we're commanding, this is going to be relative to the fuel type that we're going to be dealing with. So different fuel types have different stoichiometric ratios that are going to be associated with it. So for example, again, if we flip through this, we go back in here, we're going to find that 6.4 to 1 is going to be the stoichiometric ratio on methanol. 9 to 1 is the stoichiometric ratio on ethanol. And then that's going to be the equivalent of essentially petrol fuel per petrol. This is also going to be pure petrol. This is going to be a different fuel blend. I don't know what or different fuel type. And this is going to be a different fuel type as well. Now, the significance here, if we're looking at all of those various different stoichiometric ratios that we're finding and we can establish here, the kind of bind that holds them all together is going to be our lambda value. The lambda is going to allow us to standardize looking at our stoichiometric ratios or what we want to go and target in terms of a target air fuel, regardless of whatever fuel blend we're on. So if we're looking at this, 1.0 lambda is going to be the stoichiometric ratio for any type of fuel. So it doesn't matter if you're on ethanol, methanol, petrol, hydrogen, propane, diesel, that is going to be what we're going to consider to be our stoich point. Now, as we start to get to these higher engine load gram per rev values, we can see that the lambda value is starting to descend. It's starting to go to a lower value. This means that we're commanding a richer mixture. If we went above 1.0, that means we're commanding a leaner mixture. So the ability to use lambda as a reference when we're talking about doing any kind of tuning or calibrating is actually going to be superior rather than worrying about these individual stoichiometric ratio values here, depending on what kind of fuel that we're on. This standardizes it so we don't need to know anything really about what that stoich point is going to be for the fuel that we're on. So we don't need to know that ethanol is 9 to 1, pure petrol is 14.7, methanol is 6.4 to 1. We don't need to know that information. If we know that we're commanding 1.0 lambda, that means that we're going to be commanding our stoich for that fuel. Doesn't matter what kind of fuel it's going to be. If we're taking a look here, and we're commanding a lower value, a lower number, that means we're commanding a richer mixture. So pretty straightforward. Now, understanding, looking at this, when we're programmed.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.